Welcome back. Today we are going to look at NetworkX. A quick introduction to NetworkX. This is a very important Python package for working with networks. It's perhaps one of the most versatile network packages around. There are a few more. There are other GUI based tools and so on. But this is a wonderful Python package that gives you a lot of ways to work with networks, visualize them and so on. So, just a quick overview of NetworkX in just one slide. It's a Python language package for exploration analysis of various kinds of networks and network algorithms. It has built-in algorithms for a lot of things that we have seen and will see in this course. And it supports various data structures for representing various types of networks or graphs, as we call them. It could be simple graphs, it could be directed graphs, it could be undirected graphs, of course, and graphs with parallel or multi edges between the same pair of nodes and so on, and also those with self loops and so on. So, we haven't really focused on these kinds of graphs in this course, but just know that NetworkX supports all kinds of graphs that are practically useful to model various real world systems. The nodes themselves can be any hashable Python object, which means you can't use things like lists, but you can very well use any other mathematical object, including classes that you define on your own. So, they could be very lightweight, or they could be, and in Python everything is anyway a pointer to an object. So, you can really put any object into the graph, and this makes NetworkX all the more powerful. And the edges themselves can contain arbitrary data. So, they are all treated as dictionaries, Python dictionaries, so very convenient to work with and very flexible, ideal for representing any kind of network that you will find in any field really. And there are many graph algorithms that are available out of the box, like say Dijkstra's shortest path, or between a centrality or clustering coefficient, or any other kind of measure you want to do, or even various kinds of graphs. You can readily generate a regular graph, or you can generate an Erdős-Renyi graph, a Barabasi-Albert graph and so on. So, these are all graphs that we will be studying at various points of time in this course, and you will see that all of these are very readily doable with NetworkX. And there are excellent unit and functional tests in the module which will also help you understand a little bit more about NetworkX code itself, and excellent documentation that you can see online. So, we will also walk through this in a tutorial mode in a Python notebook, but just sometimes it is also helpful to look at code and just commit some of these basic syntaxes to your head. So, import NetworkX as NX. So, this is the standard way you would start any NetworkX, any program that uses NetworkX, and G equals nx.graph, and you add node. You can add either a nodes of any type really. You can see that here, right. So, you can add an integer node, or you can add a string node, and you can print the nodes where it shows a list of all different types that can be mixed. And this is an advantage of Python, and NetworkX naturally inherits it. And what are all the methods that the graph object supports? You can do g.vertex count, it returns the number of vertices. G.vertices will give you a list of vertices. Edge count obviously gives you the edge count. Edges gives you the list of edges. Get edge is very useful. It checks if a particular edge exists or not in the graph. And similarly, degree tells you if what is the number of neighbors of a given node, and typically it gives you the out degree if it is a digraph, but it's in an undirected graph, it will give you the full degree, so to speak. And it also there are also methods that support the extraction of incident edges. Right. So, what are all the edges emanating from a given vertex, right. So, either you can see that you can either use out equals true or not here, and you can insert any vertex that you want, and you can insert an edge and with certain kinds of properties whatever you want and so on, and you can remove a vertex, remove an edge and so on. So, these are the extremely basic operations that you will do with NetworkX, and we will review all of these shortly in a tutorial as well. The nodes themselves can be anything. For example, you can even add a function or something like that. Not that you would find many uses for this, but you can really add any kind of node. and you can even add a file handle as a node, and so on. And I can add any kind of attributes I want to add to the nodes, and it is very nice that these will all go in as dictionary entries, right. So, I can then retrieve the node and I can start looking at what are its features, what is its label, what is its it could be a confidence of an interaction and so on. We will see more motivating examples shortly. And the edges are just pairs of nodes, and they are represented as tuples of nodes. They can just be added simply just add a pair of nodes. So, g dot add edge 1 comma a, g dot add edge b comma math dot cos, any kind of arbitrary nodes you can add, and but you cannot add a list, right, because a list is not a hashable element. So, it throws an error when you try to add a list using the g dot add node function, right. And if the nodes do not exist in the graph, they are automatically added to the list of nodes. So, suppose so you can just, you do not need to use add nodes typically, you can just use add edge and it will automatically add the nodes to the graph and also connect them as an edge in the graph object. And the edges can also hold arbitrary data. So, any Python object is allowed as edge data. It could be a number, a string, a file, an IP address, whatever. Probably the most useful edge data types are numbers and strings, but other objects may also be useful because you may have edges representing more complex objects and things like that. So, the edge data are assigned and stored in a Python dictionary, which is by default an empty dictionary, and you can use various kinds of algorithms. For example, here we have added weights here of say 0.3, 0.5, 2 and 1, and now when you find the shortest path from A, it can actually give you all the shortest paths and their distances. So, there are various ways in which you can look at the shortest paths. So, you can either do a weighted shortest path or an unweighted shortest path. So, if you look at this graph, the unweighted shortest path from A to D is through C, right. So, A, C, C, D, just 2 edges. So, think of all the weights as being 1.0, but then if you want to find the shortest weighted path or weighted shortest path, what you will see it is A, B, C, D, simply because AC is a very expensive edge, right. So, AC is has a weight of 2, and remember all these edges are like costs. So, higher edges, higher edge weights are bad in general. And there are other many simple properties like what is the size of the graph in terms of number of nodes, what is the order of the graph, what are the number of edges in the graph, and there are ways to iterate over the edges. So, you can say for E in g dot edges iter, you can do something with all the edges, you can process all the edges in whichever way that you want and so on, and you can even add a path directly and things like that. And drawing, this is not the most, this is not the greatest strength of NetworkX, but nevertheless it is often useful at least for visualizing simple graphs, and this leans on matplotlib. You must be familiar with NumPy, matplotlib and so on, which are like some of the big pillars of Python. And what you see here is that there is a very simple way to draw these graphs. So, just say G is nx dot circular ladder graph. So, this is like a ladder graph you can see. So, like every pair of nodes is connected. So, you can connect I and j if I minus j is 12, right. So, that is what you see here, and of course, or if I minus j is plus or minus 1. So, that is also connected here, and then you just say nx dot draw g, and which uses matplotlib under the hood to make this illustration. And these are other graphs from the NetworkX documentation and elsewhere. You can see that there are very many ways in which you can visualize these complex networks and so on. And there are various visualization algorithms as well that are typically used, and there are different other tools also that can be used for visualization. We will try to look at them a little later on in the course. Now, there are some limitations as well, starting with visualization. It is really not the best for visualization, and you can really check out tools like Cytoscape, Gephi and things like that. And it may also struggle with very large networks when you are talking about millions of nodes and billions of edges, because in some of these cases you are almost hitting the limits of Python itself. you're probably better off using C or something like that, simply because Python itself has a little bit of overhead because of its simplicity and things like that. So, the Python objects can start becoming very, very large and unwieldy, and when you want to be really frugal and fit in very, very large graphs in memory, you may not really be wanting to use Python and so on. So, these are things to think about. And going back, edges are just pairs of nodes, and there are no custom node objects or edge objects in NetworkX, and it takes a very node centric view of the network, and nodes are basically anything you put in that is hashable. It could be any Python object, it could be a number, it could be a tuple, it could be whatever, and edges are basically tuples with 2 nodes, and anything else is a dictionary. So, you could store weight or you could store other properties, and they are all stored in a dictionary, and you can define custom node types and so on as well, right. And remember, NetworkX is all Python, and you focus on computational network modeling and not on software tool development and so on, and you can really quickly adapt it to various algorithms or models. And here are some simple graph generators. You look at a complete graph, a complete bipartite graph, a Barabasi-Albert graph, a Watt-Strogatz graph, hypercube graph, and so on and so forth. You have all these kinds of interesting graphs that you can readily generate using NetworkX. And NetworkX has an excellent documentation. So, you can just doing this will give you a long list of all algorithms in NetworkX and their summary. So, you can use that to figure out what algorithms are already available for you, and how you can readily use them in your work. And you can also implement new algorithms, because it is a very well featured package and very easy to use package with all the properties readily accessible and so on. So many centrality measures, they are all directly implemented. So, we will go back to another tutorial, and we will take a closer look at NetworkX, wherein we will run all these commands and see how easy it is to work with these graph objects in Python. Thank you.